Hello and welcome to Dr. Jim's Structures class,
Man's practicing fuzzy math again.
where we do structures by example. This video covers the key concept of free body diagrams. And to make sense of structural analysis, you simply have to understand free body diagrams. In fact, this may be the most important lesson in structures you'll ever learn. Just saying. So, let's get to it. You might be thinking, just what is a free body? Well, it's simply a structure, or part of a structure, cut away from the rest of the world, and it is in equilibrium under the action of a set of forces. It might help you to think of the free body as floating serenely in space in equilibrium under the forces acting upon it. These forces must include any internal forces that have been exposed by the cuts made to produce the free body. In other words, the cuts externalize the internal forces, and because they have been externalized, they must be included in the equations of equilibrium. Other forces include applied loads and self-weight. Dr. Jim teaches structures by example. So to see how all this works, we will consider a 15 kilonewton weight suspended by a uniform rod. The rod weighs 2 kilonewtons and is pinned at both ends. By inspection, the rod carries only axial force, and our task is to find the axial force halfway down the rod. Now you can probably figure out the force halfway down the rod without calculation. You should also be able to figure out the magnitude and location of the maximum force on the rod. I suggest you pause the playback and give it a try. If it doesn't work out, don't worry, it's early days. So this is a trivial example. However, it's invaluable because it will illustrate all we need to know about free body diagrams. Finding the unknown reactions and unknown internal forces in structures is a branch of structural analysis. And you should be aware that the reactions and internal forces are invisible until exposed by cuts made to produce a free body. So what I'm saying is that you must make cuts at the points where you want to find reactions and internal forces. And to help visualize this process, Dr. Jim has come up with the concept of the free body diagram bubble. And believe me, it's genius. The trick is to draw a bubble that produces a free body by cutting the structure at the points where the unknown forces are to be found. The bubble's a closed shape, and the substructure enclosed by the bubble is the free body. Yep, it really is that simple. Here we're interested in the unknown force halfway down the rod, so we need to draw a bubble cutting the rod at that point. The substructure inside the bubble is our free body. Next, draw the portion of the structure that's inside the bubble. We must now show all of the forces acting on the free body, including self-weight. So there's a 15 kilonewton force due to gravity acting on the weight, and there's a 1 kilonewton force due to gravity acting on the lower half of the rod. Now we need to consider what's happening at the cut. Obviously, if we simply cut through the rod, the weight would fall to the ground. By cutting the rod, we'd have released the internal force that was stopping the weight from falling to the ground. However, if we apply the unknown internal force that was in the rod before it was cut to the face produced by the cut, then the free body will not know it's been cut away from the rest of the world. Think of the cut as exposing the unknown internal force in the rod. I've assumed the unknown force to be tensile, so it will act upwards as shown in the diagram. And should the actual force turn out to be compressive, then the analysis will tell us by giving it a negative value. We now have a free body diagram. Woohoo! And as the free body is in equilibrium, we can apply the equations of equilibrium to it. Here there are only vertical forces so only vertical equilibrium is meaningful. When it comes to writing down equilibrium equations, always start by saying what you're doing. So start by stating that vertical forces must sum to 0. Next state that upward forces will be regarded as positive. That's the sign convention to be used for this equation. There are 3 forces involved: the gravitational force on the load, the gravitational force on the lower half of the rod, and the unknown tensile force T in the rod. Putting this together and solving shows T to be plus 16 kilonewtons. It's positive, so our assumed force direction is correct. That is, the force in the rod is tensile, and that completes the analysis. But wait, there's more. There's more to be learned from this simple problem. From what we've done, I hope that you have realized that it's possible to draw a free body diagram for any part of any structure. For example, let's try drawing a free body diagram for the top half of the rod. First, draw a free body diagram bubble that isolates the top half of the rod. The bubble cuts the rod at half height, exposing the internal force we're trying to find. That's good. But it also cuts the structure at the support, exposing the unknown reactive force. That's not so good. Next, draw the free body created by making the cuts. Of course, we must include all of the forces acting on the free body, and these are the 1 kilonewton force due to gravity acting on the top half of the rod, the internal force on the rod exposed by the lower cut, and the reactive force exposed by the upper cut. Again, only vertical equilibrium is meaningful, and we see that there are 2 unknowns: the force on the rod T and the reaction R. One equation with 2 unknowns has no unique solution, so we're stuck. The lesson here is that if we're not clever about which free bodies we draw, we'll expose more unknown forces than can be found by the equations of equilibrium available to us. And this means we'll not be able to solve for the unknown forces. Now, this is a very important observation. I'm hoping that you're thinking, but we know the force in the rod from the previous analysis. And if you are, then well done. To proceed, we need to realize that a cut produces 2 cut faces. Obvious or what? But what's less obvious is the fact that the forces acting on the 2 faces are always exactly equal and opposite. The reason for this is that the forces acting on the 2 cut faces must affect the structural element in exactly the same way. This is another key concept. The first analysis showed the force at the cut to be 16 kilonewtons acting upwards, and this means that the force on the other face of the cut must be 16 kilonewtons acting downwards. In other words, the force on each cut face must produce tension in the rod. It must be this way. Think about it. And knowing this allows the result from the first analysis to be plugged into the second equation, and solving that equation shows the unknown reactive force to be 17 kilonewtons upwards. Note, this is the same as the maximum tension in the rod. This second analysis has been educational. It has shown us that a free body diagram can be drawn for any part of any structure, but the unknown forces can't always be found. This happens when more forces are exposed than there are equations of equilibrium. We also learned the key fact that the forces acting on the 2 faces produced by a cut must be exactly equal and opposite. Although this is a trivial example, the concepts covered are extremely important. Free body diagrams are an essential tool of the structural analyst, and free body diagram bubbles make drawing free bodies simple and foolproof. If you don't understand free body diagrams, or choose not to use them, then I guarantee you're in for a world of pain. Just saying. If you would like an annotated printable copy of this solution, then head over to Dr. Jim's website at drjimstructures.com. There's a link below. And if you found this video useful, please give it a like and consider subscribing to Dr. Jim's Structures channel. And feel free to comment below. Your feedback is appreciated. Well, thanks for watching and bye for now. I hope to see you again soon.
Phony numbers.
If I could respond to that.
Let me just tell you what the facts are.